Last time, our elimination ended with a warning. What if a pivot dies? What if a whole row turns to zeros? Today we find out, and the answer is a complete map of everything that can happen to a linear system. Remember the picture from video 1. 2 equations, 2 lines. Usually, the lines cross at exactly one point. One solution. But they can also be parallel. No point in common, no solution. Or they can be one and the same line. Every point works, infinitely many solutions. 1. None. Or infinitely many. These are the only 3 possibilities for 2 unknowns, or for 1,000. Let's see how elimination tells them apart. Back to the workshop system, the one we solved in the last video. We keep the first 2 equations exactly as they were. But the third equation, we now replace with a brand new one. And look closely at it, it is exactly the sum of the other 2. Whatever the first 2 equations already say, the third just repeats. It brings no new information. Let's find out what elimination has to say. As always, we first translate the system into its augmented matrix. The coefficients go on the left of the bar, and the right-hand sides after it. Swap rows 1 and 2, to get a 1 as the first pivot. Subtract twice row 1 from row 2. Subtract 3 times row 1 from row 3. And one last move. Look carefully, rows 2 and 3 are now identical. So when we subtract row 2 from row 3, the whole of row 3 is wiped out. 0, 0, 0, and 0. As an equation, the last row now reads 0 equals 0. Always true, and completely empty. We can simply drop it. So one of our equations was redundant, and elimination has just exposed it. We are left with only 2 independent equations, for 3 unknowns. 2 equations can pin down 2 unknowns. The third one, x3, remains free. For every value we choose for x3, the other 2 adjust and give a solution. A different choice, a different solution. That is infinitely many. Geometrically, the 2 remaining planes meet along an entire line. Now, a small experiment. We keep every coefficient, the left-hand side stay exactly the same, and we change one single number on the right, the 21 becomes a 20. Since the coefficients are the same, elimination repeats itself, move by move, the same swap, and the same 3 subtractions. Only the column on the right of the bar can come out different. Now look at the last row. On the left of the bar, 0, 0, 0. But on the right, -1. Read as an equation, it says that 0 equals -1. And that is not an empty statement. That is a contradiction. No choice of the unknowns can repair a contradiction, the unknowns don't even appear in it. So this system is impossible. Geometrically, each pair of planes still meets in a line, but the 3 planes together have no common point. No solution at all. Let's line up the 3 systems we have met, each already reduced to its staircase. On the left, the workshop system from the previous video. In the middle, the system whose third equation was redundant. And on the right, the very same one, but with a single number changed on the right-hand side. For each system, look only at the coefficient part, everything to the left of the bar, and count its pivots. That count is the rank of the coefficient matrix A. On the left, 3 pivots, so the rank of A is 3. In the middle, only 2. And on the right, again 2, the coefficient part is identical. And these ranks decide everything. Rank 3, matching the 3 unknowns, 1 solution. Rank 2, leaving 1 unknown free, infinitely many. And rank 2 on the left, but with that stubborn contradiction on the right, no solution. We have already measured the rank of A. 2 more quantities complete the picture. N is simply the number of unknowns, here, 3. And the rank of a bar B counts the pivots of the whole augmented matrix, this time including the right-hand column. Watch the third staircase again, that -1 is a pivot 2, sitting in a row of its own. So while the rank of A is 2, the rank of a bar B is 3. That gap between the two is exactly what a contradiction looks like. With these names, the Rouchet-Capelli theorem almost states itself. If the rank of A is smaller than the rank of a bar B, there is a contradiction, no solution. If the two ranks are equal, and equal to n, every unknown is pinned down, exactly one solution. And if they are equal, but smaller than n, some unknowns stay free, infinitely many. So the augmented matrix tells the whole story. But until now, matrices have been pure bookkeeping, tables that hold numbers while we do the work. It is time to let them come alive, add them, multiply them, give them an algebra of their own. That is the next video.